Lesson 4.3, operations with polynomials. So this doesn't look a whole lot new. All we're doing here is saying, okay, what's a polynomial? What's the degree, right, which you guys have been doing? Can you add polynomials? Can you subtract polynomials? Can you multiply polynomials? And then there's some fun word questions like the volume of this cake. Okay, so I highlighted a bunch of these ahead of time. Yeah, some of these are word type puzzles down here. And yeah, we solved a bunch of these with you guys. And then now lesson 4.4 is dividing polynomials, okay, which often seems like a bit, but this one's a little trickier, a little more involved, so that'll be its own lesson. All right, so let's go through here. Okay, we got a binomial is the sum of two monomials, so a monomial has like one term, right? Bi means two, trinomial, like tri is three, so like three monomials. A polynomial, you guys got poly is many. A set is closed if and only if an operation on any two elements of the set produces another element of the same set, because adding or subtracting polynomials results in a polynomial. The set of polynomials is closed under the operations of addition and subtraction. Okay. I don't think that'll be the case when we get to dividing polynomials. If you divide two polynomials, it doesn't necessarily result in a third polynomial. Sometimes it might, but not always. All right, so here, skip through here. Let's go straight to adding polynomials. Okay. So here we're going to add like terms. Here, I'll just point this out because they've got this pretty well solved right here, or a lot of it. Right? And then in the main text puzzles, I'll do some of these. So I see 6x to the 3 here and an x to the 3 here. So we're grouping all these plus then the group of all these. Right? But you can just add the x to the 3 terms, and I see 7 of those. Right? 6 here and 1 here. So it should have 7x to the 3. You know what? Actually, I didn't quite write the answer, so I'll write it. So this is example 2. Okay. Yeah, and actually, we'll just go ahead and write this out. 6x to 3, because I have larger font anyway. 7x squared minus 2x plus 5. And we're going to add, kind of running out of room. Let's go have it down here. X to the 3 minus 4x squared minus 8x, and then plus 1. Right? Well, if we're adding these together, right, maybe it's actually even easier to see this way. 7x to the 3, 7 minus 4, that's like 3, and that's x squared. And so we got x squared terms. So as long as it's like terms, we put them together. Negative 2x, negative 8x makes negative 10x. And then the constants add together, 5 and 1 is 6. That's the answer. That's all. So boom, done. Subtracting polynomials. So example 3, subtracting polynomials. All right, so we have 2x to the 5 plus 11x to the 4 plus 7x and then minus 8. Okay? And we're going to subtract all this polynomial. So minus, and then in parentheses here, I got 5x to the 4 plus 9x to the 3, then minus 3x, and then plus 4. Okay? Now, the fact that I'm subtracting off this whole expression, can I just distribute this negative, make this a plus, and then minus, minus, and then this changes to a plus, and this is a minus? I could do that. Okay? So you could add the negative value, but yeah, anyway. Now, I only see one x to the fifth term, and that's right here. So I have the whole thing left over, 2x to the 5. I only see one x to the 4 term, that's right here. And I'm subtracting that, so I have to say minus 5x to the 4. Oh, wait, no, that's not right. There's another one up here. I'm getting silly. So 11 is something minus 5 is something gives me 6 of that thing. There you go. You combine the x to the 4 terms. Okay. There's only one x to the 3 term, that's right here. So minus 9x to 3. There's two x's, so it's 7 and 3 makes 10x. And then negative 8 minus 4 is negative 12. Okay. So that should be the answer right there. Okay, boom, double check. I think that's right. Yeah, okay, that was right. Yeah. And so adding, subtracting, you just add like terms or subtract like terms, except the like terms can go together. Okay, but that's like as simple as you can make it for standard form. Okay. How about multiplying? Okay, so this is they say distributive. Now, if there's just one term in here, like the example for, if I have 1/2 x and I multiply that this whole expression on the inside, 4x to the 3 plus 5x squared minus x minus 7. What I can do is take this 1/2 x and multiply it into each one of these four terms, right? And you get the answer that way. So half x times 4x to 3. Well, half of 4 is 2, and x times x to 3 is like x times x times x times x. So that's 4x's. Right, plus half of 5 is 5 halves. X times x squared is x to the 3 minus half of x squared, and then minus 7 over 2, and then x. Okay, that's it. Boom, done. Now, example 5 is a little trickier because, okay, now we got like a whole expression times a whole expression times another whole expression. Some more paper for this one. So, example 5, right, what if I have 3a plus 5, a minus 7, and 4a plus 1. Right, so a, you can think of kind of like x, it's the same idea. Right? I think I need to FOIL these first two expressions first, outside, inside, last. Right? And I'll worry about this one later. Right, so let's start with this. So first, we got 3a squared minus 21a plus 5a, and then minus 35. Okay, now it's all multiplied by this 4a plus 1. Okay? And before I take care of that, I can't clean this up a little bit because I do have two a terms, so I can tag those together. So let me go do that. So I got 3a squared. Now, negative 21 plus 5, I think it's negative 16. Those are a's, and then minus another 35 here. So that's a simplified as can make this part. And this is all multiplied by 4a plus 1. All right, there. All right, now I have sort of a super foil showing up. So this has shown up a few times before in this class, where maybe I'll take this expression on the right and multiply it into everything on the left. So I need to distribute for each one of these terms, and I can add it together. So this 4a gets multiplied by the 3a squared, and also the 16a, and also the 35. Okay. After that, this 1 gets multiplied by, switch to blue, this 3a, and also, sorry, that's 3a squared, right? And also the 16a, and also the 35. Okay. So I can have up to 6 terms. Now, some of those might consolidate, okay, but we'll do that first. So I'll get 6 terms right here. So 4a times 3a squared, that would be like 12a to the 3. Then straight over here, 4 times 16, 16, 32, 64, 64. So minus is minus 64. A times a is a squared. Right, next, 4 times 35. Well, 130 times 2, 35 times 2 is 70. Times 2 is 140. And subtracting. So minus 140a. That's that. Okay. The next one, okay, plus 1. Oh, no, this 1's nice because 1 times anything is itself. So I have a plus 3a squared. I have a minus 16a. And I have a minus 35. Okay. So there you go. Just like I said, 1, 2, 3, 4, 5, 6 terms. Okay. And so can I consolidate these? Yeah, these two are both a squared, and these are both a. So I can tag those together. So I still have 12a to the 3. That's by itself. Right. Now, what is this put together? I think it's minus 61a squared. Minus 61. So minus 61a squared. That comes from this one and this one put together. Okay. Then these two are going to combine to make, what does this make? Negative 156 a's. And then you still have this minus 35 out here. Okay. So I think that's as much as I can simplify this. So that's standard form of a polynomial for the answer. Yeah, just like that. It's like kind of like a super foil, right? It's like foil plus kind of thing. Right. Yeah. So whenever you have a bunch of terms added together, and then a different set of terms added together, and you're multiplying those two expressions, you have to take every individual term and multiply it by every other individual term from the other expression, right? So FOIL foil is kind of it's like 2 terms times 2 terms, so it's a simplified version of that. All right, so got that. All right, and then last example, it's a word puzzle. Yeah. Byron is baking a 3-tier cake, 1, 2, 3, for a birthday party. Yay! Each tier will have half the volume of the previous tier. This kind of looks like that. It looks like the tiers are getting smaller in volume as they go up. The dimensions are shown. Now, they write the dimensions in terms of x. That's interesting. Maybe there's some reason for that. find the total volume of the cake. Again, it's going to be in terms of x. We don't know what x is, but we have to calculate for something. So I'm going to calculate the volume of tier 1, and I'll say the total volume, they would say V total is the volume of tier 1 plus the volume of tier 2 plus the volume of tier 3. Right? So the total volume is the sum of the 3 volumes. Okay? Oh, you know what? Actually, I can kind of simplify this even before I get to all the x's. So V total that we're looking for, whatever the first volume is, plus, okay? Isn't V2 half the volume of V1? So it's like half of V1. And isn't V3 half of V2, and which is itself half of V1? So it's half of a half. That's like a quarter compared to the original V1. You see it's got to be like that? Actually, I can add these together. You can get a common denominator. Let me do that. So yeah, I'm just working in terms of the volumes. I haven't even got to x yet. So is this like 4 over 4? Is that okay? So 4 over 4 V1 plus, and half is like 2 over 4 V1. And this is 1 over 4 V1. I'm just getting a common denominator, in this case 4, so I can add these together. 4 something plus 2 something plus 1 something. I'll show you guys little pie charts too. So if I had 1, 2, 3, 4 quarters, that's like just V1. Here's 2 quarters, or half if you like, and then 1 quarter. Okay, so if you didn't see it before, how to add fractions, you can see it now. We've got 4 quarters, 2 quarters, 1 quarter. It's not like 7 quarters. Okay? So the total volume is going to be 7 quarters of whatever the volume of tier 1 is. Right? So we figured that out. That's all just from this bold section up here. Okay. Right, now if you look at this diagram, we can figure out what the volume of tier 1 is in terms of x. Isn't volume length times width times height? So volume of tier 1, back to just tier 1, or this one, here, is this base, which is 4x minus 3, times this depth, which is 2x plus 1, times this height, which is x. Yeah, you do that. Right, now, if I slap on a 7 over 4 in front, I have volume of the whole cake. Now, that could be the answer. If this was asked on Alex, they might want you to go ahead and FOIL this out and put it in a standard form. So I'll go ahead and do that too. Yeah, it might be a little more to do. I go first, outside, inside, last, and then later on I can bring this x into play. Okay. So volume 1 equals, so 4 times 2, I got 8x squared, then plus 4x minus 6x, and then minus 3. This is all times x. Just like that. Okay. So clean this up again. Okay. Okay. I'm going to do 2 steps in one. Okay. First of all, can I combine the 4x minus 6x to make negative 2x? Okay. At the same time, I can take this x right here and I can multiply into each one of these terms. Okay. So that's going to give me volume 1 is, okay, 8x to the 3. Ooh, 8x to the 3, because x squared times x to the 3. Okay. Now this was negative 2x times this x gives me negative 2x squared, and this is minus 3x. Okay. So remember, that's the volume just of tier 1. If I want the total volume right here, all I have to do is take this tier 1 and multiply by 7 quarters. Okay. I could distribute that across all 3 of them, or I could have it outside a set of parentheses for this whole thing, however I did. So V total, the total volume of this cake is, or go ahead and multiply it in. So what's 7 quarters times 8? Well, 8 divided by 4 is 2, times 7 is 14. I think it's 14 x to the 3. Let me double check my work. So if I have 7 quarters times 8, yeah, that's definitely 14. So got that. And that's x to the 3. Now 2 over 4 is like half times 7. It's like 7 halves. So minus 7 over 2 x squared. I double check my work. 7 over 2 times negative 2 is, so 7 over 4. So there you go, negative 3.5, which is negative 7 halves. Okay, so we're good. And then minus, well, I think this last one, 3 times 7 is 21 over 4. So we go 21 over 4. That'd be x. Okay. So yeah, there's the total volume of the 3-layer cake, just in terms of x, which is just straight off this picture of the book. Okay. So just like that. There's all the examples. So let's jump into some of these. Okay. I'm going to pick a few from each of these sections here. Right. So the first section says determine whether each expression is a polynomial. If it is, take the degree. Right. So here, let's do the first four. Yep, the first one is a polynomial. Uh, so yes, polynomial. And the highest power on x is 2. So the degree 2. Right, next, number 2, right here. Here, oh, right, so 2x squared minus 3x plus 5. Okay. Number 2 goes a to the 3 minus 11. Okay. So yes, that's a polynomial. And that's degree 3 from this power right here. Number 3. Uh, 5nt over n squared. Now I can simplify that as 5t over n because one of the n's cancels. And then that's minus 2g over h. Well, because if you have variables in the denominator, then that right there, because of that, so I'm pointing to the reasoning, right? Not a polynomial. Remember, you're not ever dividing by x, or in this case, n or h, right? Or you could say x or n or h would not be raised to negative powers, which gives the same result. So not a polynomial. And number 4, square root n minus 7. All right, so you see a square root, right? You'd say, also not a polynomial, right? Because of that reason. This is, by the way, same thing as n minus 7 to the 1/2, right? But it's still, not a polynomial. Let me show you guys that's true. What if I plug in, let's say 16? What's the square root of 16 minus 7? No, 16 minus 7 is 9. So square root of 9 is 3. Yeah, so you get 3, right? Okay. What if it says square root, what if I do a 1/2 power? What if I do 16 minus 7 to the power of 0.5? Hey, it's the same thing. Yeah, right, but still not a polynomial. Okay, number 5, add or subtract. So I pick the subtract one and then add one. I say number 5. I got 6a squared plus 5a plus 10. So there's one expression. And I'm subtracting this other expression. 4a squared plus 6a plus 12. Like that. Okay. So remember, you're allowed to add or subtract like terms. And another way to think of this is you could distribute this negative. So if I want to, I could do plus, minus, minus, minus. So what's 6a squared minus 4a squared? That would be 2a squared. What's 5a minus 6a? Well, that would be negative a. And what's 10 minus 12? That'd be minus 2. Boom, done. Number 9. I've got x squared minus 3x minus 3. And plus, then 2x squared plus 7x minus 2. Okay. All right, well, this is all set up to add, so that's nice. So x squared plus 2x squared is 3x squared. Negative 3x plus 7x is 4x. Negative 3 minus 2 is negative 5. Boom, done. Yeah. Number 19. Oh, now we're multiplying. So I picked a couple here to multiply. Yes, this is like that superfoil scenario that we were looking at earlier. So I've got x minus y all multiplied by x squared plus 2xy plus y squared. Okay? And so my strategy is going to be this. I'm going to take this x and multiply by that term, that term, and that term. Then I'm going to turn around and take this y and multiply by that term, that term, and that term. Okay? So I'll get 6 terms, then I can add the terms together, and some of them I consolidate, but we're going to see. So one step at a time. X times x squared, that's x to the power of 3. X times 2xy. Well, the x's combined, so that's 2x squared y, right? And then x times y squared, well, that's just xy squared. Right, so there's 3 terms. So what's going to do? So negative y times x squared, so that's negative x squared y. Okay, negative y times 2xy, that's minus 2xy squared. And then negative y squared is negative y to the 3. Right, like that. So one step at a time. Right now, do these consolidate? Oh, okay, I see a couple of x squared y terms here. So this and this I can combine. Also, xy squared I see there and also there. So I can combine these 2 pink terms and these 2 blue terms. let's try it. So I still have x to the power 3. Now 2x squared y minus x squared y leaves me with 1x squared y, or just x squared y, like xy squared minus 2xy squared leaves me with a negative xy squared. And then I have minus y to the 3. Okay. So it's sort of like a standard form. I think that would be simplified there. I wonder if that could be rewritten any other way. There might be a way, but I think that's good enough right there. Number 25. Here, I better go landscape on this. I guess this one's about to get exciting. I think I'm about to have 9 terms on this. 9 terms. So 25. I've got x to the 3 minus 3x squared plus 1. And that's all multiplied by 2x squared minus x plus 2. Ooh, 3 terms here, 3 terms here. Okay. So in terms of a strategy, we'll start with Blackie. This x cubed is going to get multiplied by this term, and this term, and this term. Switch to pink ink. This 3x squared, which is negative, gets multiplied by this term, and this term, and this term. Then blue ink, this 1 gets multiplied by this term, and this term. Okay, 3, 6, 9. So I'll have 9 terms. Okay, see if I can fit them on with this page. You're going to see. So x3 times 2x squared. Well, there's a 2, and then x's, I have 1, 2, 3, 4, 5. So 2x to the 5. Right, there's my first term out of 9. Right, next one, x3 times negative x, that's negative x to the 4. Right, next one, x to the 3 times 2, that's plus 2x to the 3. Yeah, so there's 3 terms right there. Right, let's go over point. So negative 3x squared times 2x squared is negative 6x. Okay, and then 2 and 2, that makes 4x's all together. So right, next, point. So negative 3x squared times negative x. Well, the negatives cancel, so I'm going to get plus. And that's 3x to the 3, right? Because 2x is there and 1x there. And then negative 3x squared times 2. That'd be negative 6x squared. Okay, and finally, let's get over to this 1. So 1 is just multiplied by this and this and this, which doesn't change what it looks like. Just multiply by 1. So that's plus 2x squared from here, minus x here, and then plus 2. Woo! Do I have 9 terms? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that looks good. Now, what consolidates? Let's see here. Do I have any x to this other than this one? No. How about x to the 4? Yeah, yeah. So this x to the 4 and this x to the 4 term, I can put those together. How about x to the 3? I see a couple of those right there or right there. How about x to the 2? Well, that would be these right here. And then there's a single x term and a single constant. Okay, so we combine the pinks, combine the blues, and then swash these guys together. Let's do it. So that gives me 2x to the 5. Now, negative x to the 4, negative 6x to the 4 brings me to negative 7x to the 4. So that's those. Right, then these guys, that's 2 something and 3 something. That gives me 5 of that. That's x to the 3. Right, then bring these together, that's minus 4x squared. Then add this negative x and those 2. Whew. Right, I think that's as simplified as I can make that. And that is standard form right there. Right. So, a bunch of little parts, but not too bad. 27, construction. A rectangular deck is built around a square pool. The pool has side length S. I'm going to pause right there and start to get a picture going. Right. So we got this square pool with side length S. You know what? It's okay if I change that to X because S's are easy to mix up with 5s. So I'm just going to change this to X. And yeah, okay, just let's call it X. So there's some pool. Maybe put little pool ripples so we know this was like water. Oh, put a little beach ball in here. How about that? A beach ball. Yay! Put in there. But there's a pool. The length of the deck, remember the deck is being built around the pool, is 5 units longer than twice the side length of the pool. And the width of the deck is 3 units longer than the side length. Okay. So I think it's going to look something like this. Okay. So this is all the deck. I just drew a rectangular deck where the length is 5 units longer than twice the side length. So here's twice the side length, then plus 5, right there. And then this width right here is 3 units longer than the side length. So whatever the side length x is, will just be plus 3. Right? It's like, what is it? Well, 3 units. If I call that meters, for example, I think that would be like 1.5 meters here and 1.5 meters here to bring you to 3 meters wider. You guys get the idea. Right? But if I want to say length equals and width equals, right, you guys get the idea. Oh, what's the question? What is the area of the deck in terms of the side length of the pole? Yeah. Right. So maybe we have to buy a bunch of wood. We're gonna put down like a bunch of wood panels. Yeah, but how much lumber do I have to buy over at the Home Depot so I can actually build this deck? Huh? Huh? Right. That's the question. Right. I'll hash it in the area. Let's say it's this pink region right here. Right? Because of course we're not building a deck over the pool water. We're just building that region right there. Right? How can you find it? Well, I can find the area of the big rectangle, and I can just subtract out the pool itself. I should make the pool blue, because water that's commonly drawn as blue. Yeah, that's a little better right there. Blue pool. So let's do it. So let's say the deck area, maybe we'll call that A for area, equals, so length times width, so that's 2x plus 5 times x plus 3. Right? But then I have to subtract out the pool water itself, which is x times x, or x squared if you like. So we got, yeah, I think that would be the correct answer. Now, of course, I can FOIL and simplify this. Let's go, yeah, let's do it. Go. So let's do first, outside, inside, last, and then we'll bring the minus x squared later. So the area is equal to, that's 2x squared plus 6x plus 5x plus 15. Right? So 2x squared, 6x, 5x, 15. And then at the end, there's this minus x squared. So there. So one last thing I need to do, I have a couple of x squared terms. I'll just combine those. So the area of the pool is 2x squared minus x squared. It's just plain x squared. Then I'll have a plus 6x. Actually, I can combine these two. What am I thinking? That's 11 of those, isn't it? We get rid of that. So plus 11x. I almost missed that. And then plus 15. Yeah, let's take that. So remember that little scratch mark there. So x squared plus 11x plus 15. Okay. Now, if this was in meters, and then this area would be square meters. If x is in some meters, this area would be in square meters. If x was in feet, then area would be square feet. Right? And they never specified what the side length of the pool is. But see, we can make that anything. Suppose we're looking for these proportions for some reason. But maybe we have small poles and medium poles and big poles, but we all want the same proportion deck for whatever reason. Then this will answer everybody's question. It doesn't matter the size of your pole. The size of your pole, if you have 20 feet across, and this is in square feet, you can just pop in 20 here. Tell you exactly how much wood to buy in square feet. Perfectly the area. Or suppose the side length was like 30 meters. You have a huge pole, like 30 by 30, 30 by 30 meters. You can pop in 30 meters here. It'll also tell you how much wood you need in square meters. Ooh, yeah. 28, volume. The volume of a rectangular prism, so this box here, given by length, width, and height. So length times width times height. The length of b squared units, width of a units, and height of ab plus c. Okay, so exactly like it shows. What's the volume? Express your answer in simplified form. Yeah. Well, I know volume equals length times width times height. Length times width times height. So the volume equals, well, where length goes, I'll put b squared. Where width goes, I'll put a. Where height goes, I'll put ab plus c. Okay. And then these are all being multiplied. Now, the b squared and a I can directly multiply. Here, I'll write it out this way. So it could be like ab squared. It's the same thing. Okay. Now, interestingly, this last piece is two terms added together. So I do have to distribute like that. So let's do that. So the volume is equal to, well, ab squared times ap. The power on a we each raised by 1. So it's like a squared b to the third. Okay? And then plus, now the c also gets multiplied by ab squared, so it's like ab squared and c. Okay? So I think that's probably what they're looking for. Okay, this is fine, this is fine. Oh, same thing. Hmm. Okay. Yeah, it looked like some of these examples were fairly similar to what we did. But 44 I thought was interesting because it's a different way to think about polynomials as like areas. Right? X is blue squared, that's like x squared, which should be base is x and the height is x. So it's x times x, hence x squared. And this one's the same thing. This green rectangle might be a base of 1 and a height of x. So it's 1 times x is x. And then what if you have no x, like 1? Can it be 1 times 1 is 1? Okay, so we have this big blue square, this tall green rectangle, this little tiny yellow square. And that could represent 2x squared, hence the two blue squares, plus 3x, hence the three tall green rectangles, plus 1 is that little tiny yellow square right there. Yeah, so that's an interesting way to think about that. Yeah. These tiles can be rearranged to form the rectangle shown. Right, but it is rectangle. See, if you just like slide these rectangles around, you can make one giant rectangle. I still got the two blue squares. I still got the three green rectangles, and I still got the tiny yellow square. But it all combines to make one giant rectangle. Uh, find the length and width of the rectangle. Find the perimeter. And okay, so they asked a series of questions. Okay, so let's make sense of this. Here, if I take this picture and blow it up, it looks like something kind of like this, right? Where there's an x squared, there's another x squared. Okay, I'm going to start over. Let's not exactly to scale. I want to get their picture pretty close. So I have x squared here, which is like x times x. I have another x squared, which again is like x times x. Okay? I have x times 1, which would give me an area of just plain x. Down here I have 1 times x, which is x, 1 times x again, which is x, and then a 1 times 1, which is just 1. Okay. So I do see that this height right here is equal to x plus 1, because this height is x and this height is 1. Okay. This width is 1, and this width is 1. And this width right here is 2x plus 1, isn't that? X plus 1, something like that. Okay. Let me show you guys that this does give the same polynomial. Okay, so the area of this whole rectangle is this width times this height, which is 2x plus 1 times x plus 1, isn't it? Okay, this base times this height, area of rectangle. Okay. Now, if I FOIL this out, first, outside, inside, last, I get the polynomial that we started with at the beginning, but it's the same thing. We're going to find out. So that's 2x squared, like 2x squared, plus 2x plus x. Well, I can just call it 3x, right? 2x and x, and then plus 1. Is that what they gave us? 2x squared plus 2x plus 1? Yeah, it's the exact same thing. It's right there. It's the same thing. Yeah, so we are doing good. And what did they actually ask them? Find length and width of the rectangle. Oh, okay, length and width of the rectangle. Well, here's one dimension, here's another dimension. So that's that answer. Boom, done. Find the perimeter of the rectangle. Perimeter. I haven't written that yet. Guys, could perimeter be just how long it takes to walk around the whole thing? So I think that'd be like two of these 2x plus 1s, because here and here, right, plus 2 of the x plus 1s, which is like here and here. Right? So there's 4 sides of this giant rectangle. Got 1, 2, 3, 4. We got 2 of these and 2 of these. Put it all together. So let me go ahead and distribute and clean this up. I can distribute this 2, distribute this 2. See what that looks like. Perimeter equals, that gives me 4x plus 2. And over here I have 2x plus 2. And then I can combine like terms. So perimeter is, that'd be 6x plus 4. That should be the answer. 6x plus 4. Okay, that's the perimeter of that looking shape right there. And select a value for x and substitute in that value so that each of the expressions above, for your value of x state, all those things. All right, so they're saying make up something for x. Like x is a variable, it could really kind of open-ended, represent a lot of things. Just eyeball this. Do you guys think maybe this green rectangle looks about 3 times as tall as its base? I think it's pretty close. I'm going to call it x3. X3. Okay. So what if this is still number 44? Continue. I'm going to say x is equal to 3. Okay, this is your choice. So I didn't get that from anywhere other than kind of made it up. Now, if that's true, then what would the area be? What would the perimeter be? Okay, so let's start with area. So area, we got was 2x squared plus 3x plus 1. But that would be like 2 times 3 squared plus 3 times 3 plus 1, which is 3 squared is 9 times 2 is 18. 3 3 is 9. 1. It's like 28 square units. So square units. Area is 28. 28. Okay. Is that true? Even if I go back to the big rectangle, will that still be true? Because wouldn't this side be equal to, here, I'll draw it up right here. See, is that still true? Right? Well, x plus 1. If x was 3, wouldn't this 3 plus 1 be 4? So I think this side would be 4. And then this side here, I got x and 1. So it's 3 and 3 and 1. Is that like 7? Do you guys see 7 right there? That's like 7. Oh, look at that! Guys, what's 4 times 7? Bing! That's 28. It's the same thing. The area is still 28 units. Yeah, look at that. And the perimeter, guys, would the perimeter be 7 here, 4 here, 4 here? Well, I see 11 and 11. Is the perimeter equal to 22 units? 22 units. Okay. I wonder if I get the perimeter of 22 units by using the expression that I had earlier, because here I'm just playing off the picture and say, well, okay, it's 7 by 4. So how about over here? If I plug in 3 for this x, what's 6 times 3? 18. 18 plus 4. Ah, it's 22. Oh, yeah, it's the same thing, as long as x is 3. Yeah. So, yeah, find a different way to think about these polynomials. You think of them in terms of these areas. That's kind of interesting. Okay, I got one more I'll give with you guys. So one more that I highlighted. 47, urban development. Ooh, so good challenge question here at the end. Questions get a little more challenging to go on. Diagram represents aerial view, which means we're up in a helicopter looking straight down. Memorial and a town center. A sidewalk 12 feet wide. Notice this blue ring has width of 12 feet. So this is the walkway, the sidewalk. 12 feet wide with an area of 384 pi square feet. Okay, that's kind of abstract. We'll work on that later. Surrounds a statue with a circular base radius r. And they don't tell us what r is, but I think there's enough information since they told us the area of this blue region where we can figure that out. Oh, actually, that's exactly the first question. Find the radius of each circle. So the smallest circle, and then plus 12 will get the large circle. Let's see, how can we figure that out? Okay, so draw their picture. Okay. But we could make some kind of expression out of this and figure this out. Okay, so here's our radius. Okay, and I know that this width right here is like 12. Well, let's say everything's in feet, right? So 12 feet. Here, I'll put feet, but everything with feet. All right, so here, I'll use blue since they were also using blue. Okay, so this blue ring right here, kind of hatched in this blue ring. Okay, they told us the area of the blue ring is 384 pi, and that's square feet. Okay. Now, playing up the geometry, I do see that this large radius right here, maybe I'll call that, how about capital R? Okay. Could capital R be equal to little r plus 12? Great, see that? Here's my little r, here's my big R, and the difference is 12. Okay. Right, so I know that the area of a circle is something to do with like pi radius squared. Pi times, I'll spell out the word pi times radius squared. Okay. So if I do that. Well, wouldn't the area of this blue shaded region be the large circle minus the small circle? And that's what's equal to 384 pi squared feet. Yeah, let's do that. So we're subtracting 2 circles, large minus small. So I'm going to say area of the ring is pi big R squared minus pi little r squared. Right? Big circle minus little circle leaves you with the ring. Right? And we have some values here, some numbers we can plug in. Okay. So I know that this right here is 384 pi. So 384 pi. Not square feet, but I'll just leave the number. Okay, I got pi. Oh, whoops, pi. Oops, there we go. Okay, I got pi. And then remember how the big radius was the little radius plus 12? I'm going to put everything just in terms of the little radius so that we're only working with one variable, in this case, the little radius. Okay? That's being squared, don't forget that. And then minus pi r squared here. So it looks like that. Okay. Yeah. Okay. Now, that's like the critical thinking part of this. Okay, so if you can get up to here, then everything else is just pretty fundamental algebra. So I think I can FOIL this out. So first, outside, uh, inside, and last. All right, FOIL right there. Okay. And then multiply that by. Actually, you know what? Guys, look at this. I have one, two, three terms. Do you guys see three terms? Can I just divide every single term by pi? That's probably why they gave us pi as part of the area. So you can very quickly just get rid of the pi's. Right? Or you could do that later. It doesn't change the answer. So that will simplify this a little bit. Say 384 equals, so that if I FOIL this, I get r squared plus 12r plus 12r, which is like 24r, and then 12 squared is 144. Don't forget, we're still subtracting off this r squared over here. Like that. Oh, look at this. Look at this. I didn't know that was going to happen. The r squareds go away. So now what we're solving for is just in one place. Okay, so that's nice. So subtract off 144. Here, I'm going to write that. Minus 144 minus 144. What is 384 minus 144? That is 240. So 240 equals 24r. Oh, look at that. How nice is that? Divide both sides by 24. So over 24, do that to both sides, balance the equation. I'm getting the little radius is equal to 10. And remember, this is in units of feet. So point, there you go. They're solved. So the small radius is 10. Okay? Now, from there, you can also get the large radius. Because remember, the width of the sidewalk is 12. So if this is 10, and this is 12, isn't this whole thing 22? And that comes from right here. It's 22. Okay? Well, I'm kind of out of space on this paper. But what do I got next? Oh, yeah. Here, I'll squeeze it in right here. I'll bring in this right here, combine with this right here. So big R equals this 10 plus this 12 is 22. Be right here. There you go. Squeeze that in right there. Because the next part is actually kind of a totally different question. They're saying a nearby town wants to use the same design concept of having some central memorial town center surrounded by some walkway. Right. But to use two squares rather than two circles. Here's 47 continued. Here's part B. So what if I kind of draw that up? So there's another concept. Ooh, I like that idea, but let's change this to like a square shape. Right. Maybe something kind of like this. Draw and label a diagram with two squares to represent a sidewalk with the same uniform width and area as a circular sidewalk. And then question C says, let S represent the side length. I'm going to change that to X, kind of like I did before. I'll change this to X. So X is the side length of the smaller square. Write a polynomial expression for the area of the sidewalk that surrounds the smaller square. Area of the sidewalk. Wait, didn't it say the same areas before? Uniform width and area. The same uniform width and area as the circular sidewalk. Yeah, okay. So B and C do kind of go together. We're both looking at this picture. Okay. If they want the same uniform width, then, well, you already know what the width is going to be because it's the same as before, which was just 12. So this would have to be 12, wouldn't it? Okay. Which means this right here is 12, and this right here is 12, and this right here is 12. These are all in feet, so 12 feet, right? I don't know what X is. Right? So this is X, X, and so on. Right? But I do know that this area, here, I'll hash it in just like I did before. This area right here has to be the same as it was before, which before it was 384 pi units. Or so it. I bet we can solve for X. Is that what it asks? Represent, draw a label, and then Well, here, we'll do as far as we can. Let's basically try to solve for x. Right? I think that's kind of a good way to go. Instead of write a polynomial and so on. So I think that this area would be the large square minus the small square. Right? Well, what is the width and length of the small or of the large square? Okay, something like this. So wouldn't this be this 12 plus this 12 plus this x? Is that like x plus 24? Right? Because x plus 12 plus 12. Okay. And well, it's a square, so this would be the same. X plus 24. Right? Okay, so I think it'd be x plus 24 squared, because base times but base times height. Okay. But also you have to subtract out the center of town memorial area, which is itself x squared, because that's that square right in the middle. So you have to subtract that out. Okay. And that has to equal 384 pi. Okay. So here, I'll bring that down here and we'll see how far we can go with this. So we got 384 pi is equal to x plus 24 squared, or I'll just write it in like a foilable form. It's the same thing as this, and then minus x squared type of thing. So now I can go first, outside, inside, last, FOIL that out. Okay. So 384 pi equals got an x squared. 24x and 24x makes 48x. And then 24 squared is 576. Right? No, I'm still subtracting this x squared here. Oh, hey, this worked out the same as it did before, where the x squared terms actually do cancel. Yeah, we can totally solve for x. Right, that's not tricky at all. Oh, I was thinking in my mind, oh, it was probably going to lead to a quadratic equation or something before. No, no quadratic equation, nothing like that. It's all right. So here, I will turn this into a decimal. I know we're having terms of pi. Let me make this a decimal and subtract over the 576. So 48x, we solve for x, equals 384 pi minus 576. Right, if you just subtract that over. Right. Here, I'll say equals, and let me get a decimal value. What's 384 pi? By the way, this is 1,206. That's a square feet. Subtract out 576. That's 630. How about 0.4? I'll just go to the nearest tenths place. Right? Then if I divide both sides by 48 over 48 over 48, right? This would also be true, right? That will give me the value of x. So x is, so take this value right here, divide by 48. I'm looking at 13.13. That's feet. There you go. I said the nearest 100. This side, here, I multiplied 48 back then. This is actually like 37 right here. That doesn't really change anything. Because still, yeah, that's it. I guess you could also find the area of this memorial in the center. Would it just be this square? I'm kind of curious to know what that is. So I'll say the small area, make a little side note here, is 172 square feet. I'm rounding to the nearest square foot. I wonder how that compares to the circular shape. Right? So I'm just looking at this little tiny square right here. It's 172 square feet. Now over here, well, I do remember we did find R before. Remember R was 10? Isn't the area of this little white circle pi r squared? Right, so that's pi times 10 squared, which is 314 square feet. So this little circle in the middle had an area of 314 square feet. That's the circular count. Now the square count, they only get 172 feet, which is 172. Yeah, approximately half as much. Right? So off by a factor of like 1.8. Yeah, right. So a much smaller area for their memorial. Ooh, if you want the larger memorial with the same sidewalk space, you want to go with the circle. You get almost twice the area that way. All right. Yeah, so that was a fun adventure. Okay. And then, yeah, so a bunch of examples, things you can do with polynomials. And the next lesson, you guys get too much to buy, but uh, that is a wrap on 4-3.